Hello and welcome to today's webinar presented by Dlubal Software. Today we'll be working in our finite element analysis and design software RFEM. The topic for today's webinar is Aluminum ADM 2015 Design in RFEM and Shape Thin. My name is Amy Heilig. I'll be your presenter. I'm the CEO of the U.S. office. I'm also a technical support and sales engineer, and we are located in Philadelphia, Pennsylvania. My colleague Wieland Gotzler will be your moderator, answering any questions you may have. He's a product and customer support engineer located in our Leipzig, Germany office. If the control panel does seem to get in your way when you logged into this GoToWebinar, feel free to show or hide it with the orange arrow up at the top. We also want to encourage everyone to ask questions throughout the webinar. You can use the same dialog box to do so. If by chance we don't get to all the questions, I will certainly send you a follow-up email afterwards. So regarding the content for the next hour of today's webinar, I want to go through the features of our standalone program Shape Thin, our finite element analysis program RFEM, and then the add-on module within RFEM, RF-ALUMINIUM ADM. We will import a custom thin-walled section that we've created in Shape Thin into RFEM, and once in RFEM, we will completely model, load, and analyze an aluminum structure. Then to take it a step further, we'll utilize the add-on module within RFEM called RF-ALUMINIUM ADM to do design of our members according to the ADM 2015 standard. So regarding Shape Thin, this is a standalone program for open, closed, built-up, or non-connected thin-walled cross-sections. So if we have unique cross-sections that we don't have available within RFEM, well, then we can utilize Shape Thin for this. Now you can create custom cross-sections with multiple materials. We can import in a Dxf file, which is what we'll do today. You can choose database shapes to create a built-up section, like from the AISC, the ADM, the CSA standard, or you can completely draw your elements yourself. Now the purpose of Shape Thin is to calculate the cross-sectional properties, and then from here we integrate this custom cross-section into RFEM with our full structure. Our other program, RFEM, is our finite element analysis program. This is where we'll be completely doing all of our modeling. Now, the modeling includes almost every material. We also integrate with BIM software such as Revit, Tekla, AutoCAD. You will load the structure and you can completely analyze it. From the analysis, we can get design internal forces, deflections, support reactions, and with this, you can take that information and utilize your own tools such as Microsoft Excel, for example, if you wanted to take that a step further to do design per a specific standard. Now, within RFEM, we can also utilize the add-on modules such as RF-ALUMINIUM ADM. This has anything to do with a specific standard and providing you that code check. So for today, for example, we will take a look at the strength limit state design for unwelded elements according to the ADM standard. But we can also check serviceability limit state design. And with those two design features, we will input a lot of other information specific to the ADM standard that we haven't already entered in RFEM, such as unbraced lengths, limiting deflection ratios, and lastly, we can optimize the members. So with that said, we can immediately jump into our first program, Shape Thin. So with Shape Thin, I want to go to File Import, and this is where we can import in a Dxf file. So you just simply navigate to the file and click Open. Now, the first thing the program asks us is to create a cross-section name. And there are three different options down here. The first is the plastic cross-section properties. I will leave this checked, so the program will automatically calculate this with this custom section. The C sub T parts I'll get into a little bit later, so we'll come back to this. And then the plastic capacity design really only has to do with Eurocode, so it's not relevant for the US or Canada, so we'll just leave this as unchecked for now. So when I click OK, I should see my dialog box that imports in my Dxf file. Now, the Dxf template options, I want to choose the correct dimensions, which would be inches here. That's what my Dxf file was created. And here would be my file from exactly the import. Now we also want to specify a reference material. So for this I can import in a new material from my reference library, and you can see over on the left we have our filters. For today I'm going to filter to metal, to aluminum, then we can filter to the ASTM, and here we have the ADM 2015. Now we have a very long and complete list of every ADM material you could possibly think of. What's also useful is to utilize your favorites group. If I check my favorites group, I've added a single material here that I can quickly access. Let's say you have several materials you access for several projects. You don't want to sift through that long list, so you can create a favorites group. For today, for this custom cross section, we'll use aluminum 6061 for extrusions, and you can see all of the material properties are given here. I click OK, and the next thing to do would be to click on a single point in this dialog box here on the left and where we want to insert it in within the Shape Thin program. So once I'm done with this, I can right click, I can expand this window, and we are now within Shape Thin. So those of you who are familiar with RFEM or other program RSTOB, the interface is identical to those programs, which is nice. So you're not having to learn a completely different process. Down here we have our tables to work with, we have our project navigator on the left, and we have our quick access tools up here at the top. So this DXF file is just simply a background drawing grid. So what we need to do, though, is to draw these thin-walled elements to essentially create the shape of the custom cross-section. But we have quite a few features within this program that allow us to do that rather quickly. Now, the first option we want to go to is this new line up here in our tools. We have a straight line selected here, but I'm going to select a thickness of 0 inches. So all I'm going to do is to snap to one of these points on my arc and snap to the other point that's perpendicular to it. Now, a lot of AutoCAD-like features such as snap points, perpendicular, parallel, that allow us to utilize these features quite nicely. So once I have drawn that, I'm going to highlight this element, I'm going to right-click, and I'm going to divide it by n intermediate nodes. Here I'll divide it by one intermediate node, and that immediately creates a center node. So now I can delete the left and right portions of the line, so I'm just left with this single node here. Now, another feature under Edit, Set Elements with Dxf Template. This is extremely useful. This has a lot of different operations that we can utilize to, again, just help us create these thin-walled elements that comprise our custom cross-section. For example, the Set Center Lines. With the Set Center Lines, all I need to do is to click 2 lines, and the program will automatically create a center line within that Dxf file template. Now, I can do the same on all 4 walls here, and the program will automatically create them. Now if I right click, I exit out of there. So let's begin drawing our elements. What I can start with is a new line again, but this time we will choose an arc via 3 nodes. Now I do want to give it a thickness of 0.25 inches. Now my reference material is already selected here, but if I did want to change it, I could do so. And if I zoom in, I will select the midpoint between my 2 end nodes. My second point will be that node that we created right there in the middle, and then lastly we can snap to the end point here. If I right click, now I have created that arc element on the left corner. In the similar fashion, we will choose a straight line. The thickness is remembered 0.25 inches, and we can just snap to the center line of that DXF background layer that we created. And we will snap to any single point on our arc element there. Now the program's smart enough to recognize overlapping elements, so we don't need to worry about accounting for stiffnesses twice or anything like that. The program is smart enough to recognize that. Now we'll do the same thing at the bottom, and we'll snap to the top. Now we could do that same process for all 4 corners, but rather we can select everything. And actually first let me utilize this tool Connect Elements up here at the top. Now the Connect Elements will make sure that all of these elements are connected to each other by placing a node on overlapping elements. So now we're going to select everything and utilize our mirror tool right next to that. With the mirror tool, we'll create a copy about the global z-axis, and then we just simply click a point graphically that we would like to mirror it around. We click OK, so now we automatically have that right side created. I will select everything in the upper half utilizing the mirror tool again, but this time about the y-axis, and I graphically select a midpoint here, and I click OK. So essentially that's all that we have to do to create this custom thin-walled section. Now, if I'm ready to calculate my cross-sectional properties, I can go up here to show results. The program says, okay, should I start the calculation? Yes, and immediately I get an error saying FY is not positive. Please check this in the table. So the program jumps to the problem where, this error was being flagged, and I immediately see that my yield strength and ultimate strength are set at 0. Well, why is that? Well, when I take a look at the aluminum material, aluminum is slightly different than something such as steel. Steel has a very clear FY and FU, but with aluminum, we have both a yield and ultimate strength for tension, for compression, for shear. So the program doesn't know which of these strengths to relate in order to calculate the plastic cross-section properties. So that's no big deal. We can just maybe relate one of those, such as the tension strength of 35 KSI to the yield strength and 38 KSI for the ultimate strength. Now when we go to rerun our calculation, everything should solve just fine. Immediately, graphically, we're shown here with our Results tab in the Project Navigator, and we can view our statical moments. Now, statical moments are the first moments of area. They're simply a product of area and the distance from the centroid. So we have QY and QZ. Then we also have the warping information. This is warping coordinates and warping statical moments. These are just geometrical quantities that are about the shear center. They're needed to determine warping stresses, so we can view this information graphically as well. Now, probably what's most important are our cross-section properties, so we can view this in the fourth table here, and here is everything that we would be needing in order to export this out to RFEM and to incorporate it with the rest of our structure. So essentially, we could save the model here and move forward with RFEM, but there's one more thing that I want to cover. In the aluminum ADM module, local buckling is checked. For those of us who've done aluminum design, we know that local buckling is very important for these thin-walled sections. So if I were to bring the shape as it is now into RFEM, local buckling will not be checked. And that's because I need to implement these C sub T elements within shape thin. And C sub T elements are just width to thickness ratios. Now, in order to implement C sub T elements, they can only be added to these straight line segments here. They cannot be added to these arcs. So if I was concerned with local buckling of one of these arcs, or had some other different shape where I had a rather large arc that I'd like to check local buckling, then it's suggested that you create multiple straight lines that compose those arc, and then you can create the C sub T elements. So back under the Data tab, I can right-click on my model name and go under General Data. And here is where I said we would get back to C sub T parts with an effective cross-section property. So I click OK, and the program automatically adds the C sub T parts over here on the left. Now, it tries to add in some of the C sub T parts, but being a rather complex section, I prefer just to select all of these and delete them and add them in myself. I think it's just a little bit more clear and show what's going on. So we have a new table here called cross-section parts for classification according to the EN. Now, completely disregard the Eurocode reference. That is truly if you just want to run an analysis and get classification for these C sub T parts. What we're doing is just adding these C sub T parts to be brought into RFEM for checking of local buckling of our wall elements. So what I will start with is right-clicking within my graphical view here, and I want to show the numbering. Under my Display tab, I'm going to scroll down to Numbering here and unselect Nodes. So now I'm just viewing the numberings of the elements themselves. So I'll begin with the left side with element 4 and 14. And the restraints, I want to check these both as restrained. This is a closed shape. Now, if this arc didn't exist and this was an open end here, then we would want to leave this as unrestrained. So that's important because when it comes to aluminum design, it depends on how the local buckling is checked. Down at the bottom, we have element 12 and 17. Again, these are both restrained. For the right side, we have element 8 and 18. And for the upper portion, we have element 2 and 7. So if I were to go and run the results again, we can start the calculation. I get an error saying no load case was defined. Well, why is that? For the C sub T elements, you have to define some type of arbitrary load. So it doesn't matter if we're bringing it into RFEM. It's just a requirement of the program that we come up here and we create a new simple load case. We don't even need to give it a description. It's dead load. That's fine. Then in our table down here at the bottom under loads, for member number 1, we're just going to give it an axial tension force of 1 kip. It truly means nothing. It's just to create these C sub T elements. So then we will go ahead and run our calculation again, and we should be right back to where we started with the results available with statical moments, with warping, but you'll notice now we do have some additional options here for stresses. That's just based on that 1 kip tension that we put in, so it's not really relevant. But we are still able to calculate our sectional properties here, and those C sub T elements are available. So now we can completely save this file, and it's important that you save the file with the results. Otherwise, in RFEM, it will tell you, it will give you an error. I'll show you in just a little bit that the results have not been ran. So we can go to File, Save, and now we're ready to jump into RFEM. So this would be our other program, RFEM, our Finite Element Analysis program. And the first thing we want to do is to give it a name, and we'll call this one whatever, aluminum 10. The model type is 3D, and we can calculate the load combinations according to the ASCE 710. I can uncheck this if I'd rather manually put in those load combinations. I click OK, and then the program will launch my model to begin. Okay, so as I said, for those of you who are not familiar with RFEM, this interface looks identical to shape thin. Obviously, we have a lot more going on, though, because we have much more capabilities within this program. But what I want to do is to begin modeling our aluminum structure. Now, I could typically start by drawing individual members, but I want to show under the Tools option, Generate Model Members, the option to create a 3D hull automatically. So you'll notice that we have many other options throughout here, but we'll begin with this 3D hull, and up pops the dialog box. So we're going to create a structure like this, all within this dialog box. So what we can do is begin by entering in some of these variables that the program's asking us for. Now, I already have created the structure before, obviously when I was practicing for this webinar, so some of these, or actually all of these variables are already input, but we'll go through them one by one. The program remembers the last settings for the file that you had open, so that's why they're already populated. So the length on the L side here, we can give it 4 bays, and then the total length, we can set this at 48 feet, so each bay will have a length of 12 feet. Now the width, which would be the front and back end here, will also have 4 bays, but we'll give this a length of 32 feet for each bay to have 8 feet. The height, we will give it 4 bays as well, which you can see it's automatically set to what we have set for the width. Now, the height of the eaves, which we can see H sub E here, we can set this to 8 feet. Now we can skip the roof pitch. That doesn't matter because it will be automatically calculated when I type in the height of the ridge H sub R of 12 feet. Coupling members is the first option here, but you'll notice if I choose purlins, purlins allow me to place these connecting these purlin members, not necessarily where the columns are, but in between them. For today, we'll stick with coupling members, which are at the column locations. Now, the support type, we have several options here. We have free, hinged, or rigid as default, but we can always go in here and create our own support type. We have the 6 degrees of freedom in both translation and rotation. We have our spring constants here for partial fixity. And then we can get into our nonlinearities. So things like partial activity, sliding, friction, well, that's really no problem at all. It's all included in RFEM if we want to get that detailed with our support conditions. For today, we will stick with the hinge type application, and then we will insert this at 0.000 within the model. Now we just simply move to the partitioning and bracing tab. For the bracing, I have this checked, and what the program will do is to place this X bracing at the bays that I specify. For example, we have the gable front here. It's asking me which bay would I like to place that in. Well, I'd like to place that in bay number 2. The gable rear will also set this to the second bay. Now the sidewall front, which would be this closest front to us, we can set this as bay number 3. The sidewall rear, bay number 3 as well is fine. And then we can also add X bracing along our roof. Again, we will choose bay number 3. Moving on to cross-section. So we've defined the geometric properties of this structure, but we now need to assign these specific cross-sections. So the first one is frame columns. That would be the front and rear columns. We will import a new cross-section from our cross-section library. So we have all of our rolled cross-sections, thin-walled, massive, timber. What's nice is that we have a lot of built-up sections as well. So any of these shapes that you see here that are applicable for your structure, by all means, utilize RFEM for it. We'll see in just a minute how we can import in our shape thin section for sections that aren't necessarily available here. Now we can also open up such as the hollow sections, and we can filter over on our left according to the ASTM and the ADM 2015. We'll hear all of our shapes directly from the standard. I can also utilize a favorites group list here. So I created a favorites group list for today's webinar, and for my initial columns, I want to utilize this 8x4 by 1/2. So that's the first section that I'm going to use. Now my material here, typically concrete 4000 PSI and steel A992 are default. But again, the program's smart enough to remember, oh, well, in the last model you used, you had these materials. So I've already added in some different aluminum materials as well. But if they did not exist, that's easy enough to import the material from the material database. And this should look familiar to what we saw in shape thin. We can filter over on the left according to aluminum, ASTM, and the ADM 2015. Then, of course, utilizing favorites group, we can add in just a few common materials that maybe we'll use for this design project. For today, we'll be utilizing the 6061 with the extrusion, but I've also added in the 6061 for bar rods and wires and for pipes and tubes. All of the material properties are given here, and we can simply add that. Now they should be available in our drop-down box. So for this one, we'll use the pipe and tube option. Now I click OK, and the 8x4 is automatically populated through all these entries. So for my frame rafters, I'm going to keep that the same as the 8x4 by 1/2. The corner columns, however, this is where I want to import my shape thin file. So in the same sense that we imported in our hollow section, down here in the lower right corner, we can import the cross section from shape thin. So if I open this up, this is where I was saying that we have some different sections maybe you've created, and if you don't save the results, you get this error, just telling you the results haven't been calculated. You must go back into shape thin, run the calculation. So for us today, though, we did save the calculation. So here is my aluminum tube cross-section. I click OK. And now the program will ask me what material would I like to utilize. Well, again, I've already added in some different materials here, so we'll choose the 6061 extrusion. So that's why in shape thin, it doesn't necessarily matter what material you use in there. You can always override it within RFEM. But here is our shape exactly how we created it in shape thin. I click OK. Now the gable posts, which would be my front and rear posts here, I'm going to utilize my shape thin. I don't need to redefine that. It's now available as one of the cross sections within this file that I can always select from my drop-down box. The gable rafters, we will we will leave this as the 8x4/1/2. Now the coupling members, I do want to import in a different section here. It will be a hollow section, but this time from my favorites list, we will choose the 3x3/0.188, and of course the correct material here for the pipe and tubing aluminum. Now, lastly, we have our vertical bracing and roof bracing. So this is our X bracing. We will create our last cross-section from our parametric thin wall. Now, all of these, all you need to do, for example, the round bar, is to put in your geometric properties, such as 1 inch in diameter, and the program will automatically calculate all of those properties for us. So from this drop-down, we can now select our last material for bar rods and wires. We click OK. And we click OK. And lastly, the roof bracing, we now have that round section available to us. Now notice the member type. The member type beam is anything that's a beam or a column. Nothing too special about that. But we do have many other options to choose from here. For example, the program automatically set the coupling member to a truss type beam or truss type member. Now this will release the moment at the start and member ends, so you only get shear and axial transfer. The vertical bracing and roof bracing, it might be quite common to set this as tension only, which is fine. I more so recommend that for something that's a cable or a rope or wire that truly doesn't have any compression capabilities at all. But for us today, since we're using a rod, it has a small amount of compression stability. So what we could set this to then is buckling. And what buckling will do is take the member out of the analysis if it exceeds the Euler buckling limit. So I suggest to do that over tension when you have a rod type member. Now the last tab is loads. You can generate some loads here. I personally am not going to use that today. I think that you have a little bit more control and flexibility when we do so in RFEM. So once we're done with all of this, we click OK, and you can see that our structure is generated. Now we will move on to loading. For this, we want to create a new load case with the quick access tool up here at the top, and the first load case, we title it dead. We do need to assign it to an action category. Action categories are important so that the program knows how to put these specific load cases into the ASCE 7 load combinations, which are important for load factors. The self-weight is automatically calculated with dead load, so we will leave this as checked. Now, creating a new load case, we will call this one Wind 1, and the action category, we will set this as Wind. Notice self-weight is unchecked because we certainly don't want to account for it twice. And one more load case, we'll call this one Wind 2 for wind in the other direction with the action category of wind. Now, the combination expressions, if we jump to this tab, the program will automatically create both LRFD and ASD load combinations. And more importantly, under the load combinations, we can see these specifically listed out. Here's our LRFD load combinations and our ASD load combinations. We'll get into this in just a little bit. So for now, I want to make sure under my drop-down box that I am under the dead load case, because now any loads that I apply will be applied under LC1 dead. So I'd like to apply a roof dead load up here, and I could apply it as member loads, but rather let's utilize some of these tools that we have. Under tools, generate loads from area loads on members via a plane. This will bring up the dialog box to apply this load. So the first thing to do is to specify the load direction, and we will apply it in the global Z direction. The program changes the picture down here to let us know exactly how that will be applied. And we're just going to apply a magnitude pretty small of negative 0.01 kips per square foot. Now the boundary area of the area load plane. So for this, what we want to do is to select first our left side of the structure, and we can do so with 4 clicks. Now, instead of leaving this application, we can also do the right side of the structure as well. So these area loads need to be in the same plane, but you can do multiple area loads within the same application. Now, I click OK, and you'll notice that all of my members, which are highlighted in red, will have the load distributed onto them based on this area load. So let's say I really only want to apply this load to my rafters and I want to disregard all the other members. Well, we can choose this members parallel to members option to remove the influence from. So for this, for example, if I want to exclude my purlins, all I need to do is to select a single purlin and all the members parallel to it will be disregarded. Now I can do the same thing for my braces with a couple of clicks here. So now only my rafters are highlighted, so those should be the only members that the load will be applied. I click OK, and then automatically I am given my area load. Now what's nice is that I can also right-click on this to display it separately, so I can see the magnitude and direction of exactly how the area load is going to be applied to my structure. Moving on to wind loads, we also have a wind load generator under Tools, Generate Loads again, but we have from wind loads for vertical walls and roof according to the ASCE 7. So with this application, we can apply wind loads for general type structures, such as this one shown in the picture here, according to Case 1 and Case 3 from the ASCE 7. We can also do the minimum wind loads from the standard as well. What we need to do is to specify a few parameters up here at the top, such as exposure category. We'll leave this as B. Is the structure enclosed? And our basic wind speed, we can leave this as 70. Now the building mean roof height for our example today will be 10 feet. And the other factors here, I will just leave these as they are. Now we need to define the base geometry and the roof geometry. It's important here to recognize how we need to define this. For example, point I on our base must be below point A on our roof. If you don't define the geometry correctly, then the OK will be grayed out down at the bottom. So that will flag you that you probably haven't defined the geometry quite right, and you can go back and adjust that. For example, the base geometry, all that we need to do is to select our 4 bottom nodes here. And then for our roof geometry, we are selecting the 6 top nodes, but we're making sure to keep the same orientation that the dialog box asks us to. Now again, we can select this option. All of the members in red will be utilized for the wind load, and if I choose to remove the influence from, you'll notice that perhaps I don't want to include my braces. Well, here's where I can unselect some of these braces, and then all the members parallel to it will be excluded from the wind load. So now we just have the influence on all of the red highlighted members. So now I can click OK, and I forgot to mention one thing. Let me double click on this. I am not going to generate Case 1 or Case 3 for this example today. I'm just going to apply the minimum wind loads according to the ASCE 7 for LC 2, which would be the first wind load case that we created. I'll set this in direction AB, which if we toggle our picture, we can see exactly how this is coming in our structure, and load case 3 will be the other direction. So just for simplicity for today's example. Now you can see those wind loads applied for LC2 and LC3. We can always right-click to group those together as an area load as well if we want to make it a little bit of a cleaner look. So realistically, we are done loading the structure. You can scroll through to these different load combinations and see how both dead load and the wind loads will be applied, including the load factors. Now, before we're ready to run an analysis, there's several features that we need to cover from the ADM. This comes from Chapter C in the ADM 2015, Design for Stability. Now, this section C2 really refers directly back to the AISC Chapter C stability requirements for the direct analysis method. I did a webinar completely devoted to going into greater detail. Today, of course, we'll touch on many of these features, but if you see something that you want to explore in a little bit more detail in regards to stability, certainly refer to our YouTube channel and AISC Design, where I go much more into stability requirements. But according to the ADM, a lot of similarities. I think if anything is unclear in the ADM, it's kind of a given to refer back to the AISC, which I'll do today. but there are a couple differences as well. There are 5 requirements that the ADM calls out for, and that's flexural, shear, and axial member deformations. That just means that the designer must determine whether connection deformations are significant and if they should take that into account with the analysis. Now, the second option is the, or not option, requirement is the second order effects of P big delta and P little delta. So P big delta, the ADM states, is included in most structural analysis software, which I think we all agree with that. P little delta, however, isn't. The ADM goes on to explain that, maybe your structural software doesn't have this, but in order to determine the required strength for compression members, P little delta must be included. Now, this is slightly different from the AISC, where there are provisions where P little delta cannot be included, depending on your type of analysis, but the ADM pretty clearly states that P little delta should be included. I'll get into how we do include both of those in just a minute. Now, the other 3 options, geometric imperfections, stiffness reduction, and uncertainty in stiffness and strength. I'll go through those in more detail in a couple minutes. So going back to our RFEM model, the question is, how do we take into account P delta effects? Well, if I go back to my load cases and combinations, you'll notice here that for my load cases under calculation parameters, the method of analysis is set to geometrically linear analysis. So this is always the case for load cases. Now, jumping to load combinations under calculation parameters, the default is to always run these according to a second order analysis. And you'll notice right in the parentheses there is P big delta and P little delta. So we do include both of those effects when you're running a second order analysis. So we have that portion of the ADM covered. Like I said, that's default for any load combinations. Now, result combinations are nothing more than an envelope solution for our individual load combinations, and the calculation parameters will always just utilize whatever we have set the load combinations to, so it will also utilize the second order effects. Okay, so that is all that we want to cover with P delta. Now, to move on to geometric imperfections, this comes from section C.2.3. Geometric imperfections are there to anticipate buckling shapes and displacements of our structure. Now, erection tolerances are not specified in the ADM, and it's really up to you as the designer to determine what those erection tolerances should be. But the ADM goes on to explain that you can use notional loads to account for these geometric imperfections, and how you do this is with a fraction of the applied gravity loads. Now, it's not too clear here on how to do that, but I think it can be said that we can refer back to the AISC for these notional load applications. And within the AISC, section C.2.2b, here is our notional load equation. It's 0.002 times alpha times yi. Now, alpha is just, depending on if we're running an LRFD or ASD design, yi is our gravity load for that specific load combination applied to that member. Now, notional load should be applied in both orthogonal directions and in both the positive and negative directions, because we really don't know the behavior of this structure under the applied gravity load, so we need to cover all of the bases. Now, the second question is, which load combinations do I apply this to? It's typical to not apply notional loads to other load combinations that have lateral loads, such as wind load, earthquake, or seismic loads. We really only want to apply these notional loads to gravity load combinations, and there are further specifications in the AISC depending on if our second order analysis over our first order analysis is less than 1.7, then we can exclude the notional loads from those load combinations with applied lateral loads. Today we're assuming that we meet those requirements, so I only want to apply these notional loads in RFEM to my gravity-only load combination. So how do we do this then? Well, it's actually quite easy. If I uncheck my loads here, and I'm going to highlight all of my vertical members here. Now, geometric imperfections really are to account for a column out of plumbness. Now, there are some other I guess stipulations that you can maybe add in pre-cameras, which we'll see in just a minute, but for today we're really concerned with column out of plumbness in terms of geometric imperfections. Now, I want to not highlight my braces here. So if I hold down my control button and select those brace elements, only my columns are left highlighted. And I can use my drop-down box to create a visibility by selected objects. Now, the next thing I want to do is I want to right-click on the member to show my local axis system of my members. You'll notice that most of them are going in the same direction except for our interior columns here. It looks like the Y and Z axis are opposite of what my columns are on my outer edges. Well, because this is a square member, it really doesn't matter if we rotate this. Now, we can do this by just by highlighting our members. We can right-click under Member to edit, and whenever we created our structure out of the structural load generator, it rotates those columns 90 degrees. Well, we can set this back to 0. We click OK, and now you'll notice that all of my local axes are going in the same direction. So why is this important? Well, if I highlight all of my members, again, my columns, and I go under Insert, Loads, Imperfections, you can see the option graphically here. Now, except for I forgot to do one thing. I am going to actually go back to my load cases and combinations, and I'm going to create a new load case. And sorry, you want to do this before going under the imperfection loads that I just showed you. So we have dead load, wind load, but we want to create a new load case here, and we'll call this one imperfection positive X. The action category will use the drop-down box imperfection. Now, with imperfection positive X, that's only one out of our 4 cases, but I'm going to start with this, this load case here. So I click OK, and now going back to Insert, Loads, Imperfections, we can choose the option graphically here. So when I open up this dialog box, you can see all my members were automatically input based on my selection here. Here is my drop-down according to the AISC 360-10. And here is our equation that should look very familiar. This is just what we saw in the PowerPoint of 0.002 times alpha times yi. Now alpha, we can choose whether that's LRFD or ASD. The yi will simply be the gravity load for that specific load combination. Now here's where I said you can add in a pre-camber if you want, which pre-cambers can be dependent on the gravity loads as well. But for this, we will forego that since we're really only concerned with column out of plumbness. Now the next question is, how do we apply this to our members in terms of the local Y or Z axis? Well, remember I named this imperfection positive X, so I'm referring to the positive global X direction, which in turn is the positive local Z direction of our members. So for this, I can leave this as the local Z option. I click OK. And now when I turn this to wireframe view and I zoom in, here is my imperfection that I have just added. So going back to the load cases and combinations, this imperfection X, I'm going to make a copy. Now the advantage of making a copy is that it will copy all of the loads that we have applied to this LC4 for LC5 as well. But this time I want to rename it as negative X. I'll make another copy of our original imperfection and call this one positive Y. And lastly, one more copy, and this one we will call negative Y. Okay, so going back to RFEM, and we use our drop-down box here to select imperfection negative X. Remember, it copied the same imperfections. We have it in the same direction, so we need to account for the negative out of plumbness now. So how do we do that? Well, we can highlight all of our members. We can double-click on this imperfection, and we simply put a negative in front of our 0.002. It's as simple as that. We scroll to the imperfection positive Y. We highlight all of our members. We double click on our imperfection here. Now our positive Y global direction is the negative local Y direction for our members. So we switch this to the local Y direction and we put a negative in front of the 0.002. I click OK, so now you can see that out of plumbness is applied in the global Y direction. Now doing this for the last time, we will select all of the members. We can scroll in to double click on our imperfection to simply change this to the local Y direction and leave this as a positive 0.002. I click OK, so now this is being applied in the global negative Y direction. We can right-click on our members to turn off the local axis system. We can go back to the wire for the rendered view here. And now you can see that we have our imperfections available. But if we go into our load cases and combinations, these load cases are here, but I jump to my load combinations and I don't see anything to do with imperfections. So how do I know that these imperfections are being applied to these load cases? Well, right now they're not. We need to specify which load combinations to apply it to. Under the combination expressions, we have this option here called imperfection load case. So what I want to do is to select this option, and up pops the imperfection load case dialog box for the settings. Here are my 4 imperfections that I define. So what I want to do is to uncheck a couple of these options. Now I want all imperfection load cases to be considered as alternative. I definitely don't want to apply all of these together as under one load combination, so they should alternate. Now the other thing I want to do is to choose this option subject to specific load cases. For my imperfections, under the option Never with Load Cases, if I expand on these details here, this is where I can select the option to never use this imperfection with any load combination that has a lateral load applied to it. So this is what I was saying in my PowerPoint. You know, if you want to exclude these geometric imperfections for load combinations that apply lateral loads, this is how you do it. Notice we did not check the dead load. So I click OK. Now I want to do the same thing for the rest of these imperfections, and if I hit my F8 key, it will simply copy the cell before it into the cell that I'm currently in. So now when I click OK, the other option I want to do is I want to select differently for each combination expression. Now for my ASC load combinations, perhaps I don't want to consider these imperfections for serviceability checks. Well, by leaving this checked, those imperfections should not be applied to ASC load combinations, but only my LRFD load combinations. So now if we jump to load combinations, we see what happened. That we have our 1.4 dead load for our LRFD load combinations, and then we have 4 additional ones where our imperfections are added. Notice the imperfections are not added to our lateral load combinations, and they are not added to our ASD load combinations. This is exactly what I wanted. So this is how you can apply those imperfections to your model. So that is all that we want to discuss regarding geometric imperfections. Now, the point number 4 and 5, which was modified stiffness and uncertainties in stiffness and strength. This refers to our tau sub E factor for flexural stiffness in section C.2.4. This completely refers back to the AISC, once again, section C3.2. This tau sub B factor is a iteration based on the equations here based on our required axial compressive strength and our axial yield strength. So this really all depends, again, on these axial loads through our member. And this tau sub B factor should be applied to our flexural stiffness. Now, the 0.8 factor should also be applied to stability stiffness, and this comes from section C.2.5. In my opinion, stability stiffness is referred to flexural and axial stiffness. There are ways to apply this to shear stiffness as well, but like I said, I think for stability stiffness and what we're concerned with today, we're just going to keep this applied to flexural and axial and not shear stiffness. So again, how do we use the program to take this stiffness modification into account? Well, back in RFEM, if we take a look at our model here and we highlight all of our members, and actually let me cancel out this visibility mode and turn off my loads here. We will highlight all of our members, and we want to right click on the member to edit it. We have a nice tab here called Modify Stiffness. Now right now the default is always set to none, but if we use this drop down, you'll see the AISC 360, Chapter C, and here is our tau sub B factor. Now when it's set to iterative, it will refer to those equations within the AISC and the ADM standard to calculate what our tau sub B factor should be and apply this to our flexural stiffness. Now the 0.8 factor down here you can see is automatically applied to both our flexural stiffness and our axial stiffness. So this will now be applied to all members, to all load cases, to all load combinations automatically. Okay, so I think that that essentially covers everything that we need to do in regards to the ADM requirements. So we are now ready to run our analysis. We can go up to calculate, calculate all, and what the program will do will run through each one of our load cases and all of our load combinations as well as the result combinations. Now keep in mind we are running a nonlinear analysis. This is also takes into account the nonlinear analysis for p-delta effects. So once this is done solving, our results will be available in RFEM, and we can see here we now have a results tab available in our project navigator. So the first thing to view here are our deformations, and we can scroll through the different load cases and load combinations to view how our deformed structure should look. Now, probably what we're also interested in is member internal forces. So we can take a look at these for any of our members. Now, for example, I can highlight this frame here and make a visibility based on only these members. We can view our axial loads, for example. We can take a look at some of our shear internal forces. Perhaps we want to take a look at these strong axis bending moments. We can always increase this member diagram. And for any of these internal forces or strains and stresses, we can always right-click on the member and we can choose a single member here, this column, and choose the results diagram. Now the results diagram is just a little application here where we can continue to add in some of these internal forces to take a look in a little bit more detail what's going on along the length. We can easily scroll between the different load combinations up here at the top. We can add these to our printout report. We can even export all of this data directly to Microsoft Excel. The support reactions are also something that's available here that we can view. So again, you can take all of this information, whether it is in these tables here or graphically, and do your own design with your own external tools. So this really sums up RFEM and the full analysis capabilities. Like I said, though, we want to take this a step further, and we want to utilize our ADM module to do aluminum design. So for this, I'm going to just uncheck the results being displayed. I'm going to cancel my visibility mode, so we just have a nice clean picture of our structure here. So over on the left are our long list of add-on modules. We also have these available here in our drop-down box where they're categorized a little bit more clear in terms of the different materials and capabilities. For example, under aluminum, we have our RF-ALUMINIUM ADM module. So for this module, it's nothing more than a dialog box. Now, I don't have to worry about remodeling any of my members, redefining materials, cross-sections. All of that is taken from RFEM. But like I said in the PowerPoint, we just need to specify a little bit more information to get that specific code check per the ADM standard. Now, there's a few things that I want to clarify before we begin. In this drop-down box, we can do design according to both the 2010 and 2015 standard. We have both ASD and LRFD. If we choose ASD and we go down into our details, you'll notice that we have the two options here for structure type. That's either building type or bridge type. But if we choose the LRFD 2015 design, we go under that details, that option is no longer there, and that's because we only do building type for LRFD design. A couple other things to note. This is something new as of just a release, maybe a couple weeks ago, local buckling. We now have 3 different options for local buckling. The weighted average method is from section F.3.1, the direct strength method is from F.3.2, and the limiting element method is from F.3.3. So you have the option here on how you prefer to check your local buckling. We feel as though the weighted average method is the most accurate method, so that's the default that is left here. Now, I won't go through every one of these details, but I do want to touch on a couple other things. Serviceability we'll actually get into later on. And under the General tab, this is where we can set the max allowable design ratio. So right now the default is set to 1.0, but for design, maybe something like 0.8, 0.7 is a little bit more realistic when we're looking at utilization ratios. And this is also relevant for optimization of our members as well. So the first thing we want to do is to go up to File, and I like to rename my case. And I'm going to call this one Columns and Braces. So we're going to design our vertical members first. I click OK. All that I need to do is to select graphically my members that I would like to design back in RFEM. So I'm just going to include all of those vertical members, including my braces. Now my ultimate limit state, I just want to select the load combinations from RFEM. You'll see all of our imperfections are available here. I don't have to redefine any of that. So there are my LRFD load combinations. For serviceability, we'd like to choose our ASD load combinations. Now we just simply need to move down the list. So our materials, again, brought in from RFEM. If you are trying to utilize concrete or steel or any other material within the aluminum module, it will give you this error invalid material. But if we take a look at any one of our aluminum materials, we'll hear all of our material properties that will be used for design. The cross sections, again, are brought in from RFEM. We can see here our 8x4 tube, and here's our shape thin section. So we can even do design of those custom sections within the aluminum according to a general type cross section. Intermediate lateral restraints. So this is just any top and bottom flange bracing, so to speak. So we can check this checkbox for lateral restraint, and you can see here member number 1, all of the tables are always synced up to our RFEM model. So you'll always recognize where you're at within your structure when you're taking a look at these different applications here. So for our lateral restraint, if we had some top and bottom flange, which really isn't applicable for our tube, but maybe you have an eye shape such as this, you can add in those restraints as a function along the length of the member. The effective length. So we check strong axis buckling, we check weak axis buckling, we also check the lateral torsional and flexural torsional buckling. Now, the buckling about the strong axis and weak axis, our effective length factor, you can see here the default is set to 1.0. Well, the ADM in Chapter C tells us that we can actually leave the effective length factor set to 1.0 when we're taking into account all of these other considerations with modified stiffness. This is the same thing as what the AISC gives us as well. So we will take advantage of that, and we will design according to Chapter C and set all of these K factors and leave them as 1.0. Now, the unbraced length, this is something that's very important. Within the program, this will always default to the full member length. And for our vertical members here, we won't be adjusting any of the unbraced lengths here, but in my next example, we will be taking a look at how we can adjust those. Lateral torsional, flexural torsional buckling. You'll notice that my shape thin sections are unchecked for this. Well, this all relates back to my details tab. Under the general, you can see here settings of shape thin cross sections. The cross section will be considered closed when our breadth torsional resistance over the overall torsional resistance is more than 95%. Now you can adjust this ratio, and then you will be allowed to do lateral torsional and flexural torsional buckling. But for now, that is the reason why these are unchecked. For a square tube-like member, torsion is probably not so much of a concern. Now for the other hollow sections here are 8x4 members. We also could uncheck torsion if we wanted to, or we can leave this checked just to take a look at it. Something that's interesting though throughout this module, M sub E, which is the elastic lateral torsional buckling moment. Well, right now the default is set to eigenvalue. So what the program will do will be to actually run an eigenvalue analysis for each one of these members to determine what the elastic buckling moment will be. So this is by far your most accurate option within this dropdown. But if you want, you can also check this option according to F, and it will use the equations from Chapter F, Section 4.2.5 to determine what that M sub E value is. Moving on to serviceability data. So serviceability data, we first want to reference our member, and graphically we can once again select all of our members at once if we want to check them all for serviceability. You don't necessarily have to check all of them though, you can just choose a few. Now we can also add in the reference length, again defaults to the full member length, but we can also manually change this if we'd like to. I'll again show that in my next example. We can add in a pre-camber here if we'd like to, and lastly we just specify whether this is a beam or cantilever. So the question is, what is this deflection check comparing it to in terms of our limiting deflection ratios? Well, that's under the Details tab again and under Serviceability. So within Serviceability, we need to define whether the deformation is relative to the shifted member ends or the undeformed system. Is this relative or absolute? For this example, we'll leave this as relative deformation. The serviceability limit, the deflection ratios, the default is set as L over 360 for simply supported members and L over 180 for cantilevers. Now, you can easily change these ratios if you'd like to. And lastly, the direction of the pre-camber that we would put in here, is it within the local Z-axis or the local Y-axis? Okay, so once we have specified those, the last table to take a look at is parameters members. Well, this is a reduction in cross-sectional area. So for member number 1 here, if we had some type of connection at the member start and or the member end where our cross-sectional area is being reduced, we can actually put in the net cross-section area here. Even more so, you can define the eccentricity of the connection in the local X and Y directions, and as well as the length of the connection. So what distance should this area reduction be taken into account for? So again, for both the start and the end, and then that new area will be used for the internal forces at that location. We won't be utilizing that today. So now that we have entered in all of this information, we are ready to run a calculation. So instead of waiting for that calculation to run, I'm going to pull up another model. It does take just a minute because of our shape thin sections, and we can jump into the current add-on module. So this is essentially what you'd see after you run an analysis. You get our results tables available here. You can view the design by load case, the design by cross section. So here we have our 8x4 tube. Here's our shape thin section, and just like what I said, because we brought in those C sub T elements, here is where those individual elements 1, 2, 3, and 4 are all being checked for local buckling. So that's, I think, a very powerful feature that we can bring in some type of custom cross section and still check something like local buckling. Now we can also view the design by member, and just keep in mind that as we're scrolling through this different table, the program automatically syncs it to our view within the background, and that big red arrow is showing you where the controlling internal forces are. We do give you the code check for a specific member for everything within the ADM. We give you all of the references directly from the code, such as A3, G1, as well as every variable that really goes into play for calculating where that specific code check came from. Now, of course, we give you the controlling down here with our green smiley face because we are less than 1.0. And lastly, we do have a material takeoff list as well. We can also view everything graphically. So if we go to our results table here, we're still within the RF-ALUMINIUM ADM. That's why I don't have any of my internal forces here. We're just viewing our code checks for serviceability, for example. And then we can view our code checks for our ultimate limit state design. Now, jumping back to the add-on module, I just have one quick last example to show you, and that would be the rafter design up at the top. I want to simply explain the difference between members versus sets of members. So I will create a new case here, and this one we will call rafters. So we're not losing any of our data from our case 1. We can always use our drop-down box for our columns and braces. So for our rafters, I want to begin by designing my members here. Along this column line, we click OK. Now my sets of members. So what is a set of member? Well, when we created this structure from the structure generator, the program places this faint red line around my entire continuous member here. This is a set of members. Now you can also manually create a set of members back in RFEM by highlighting it, right-clicking, and choosing to create set of members. But essentially, this entire rafter will be designed as one continuous member. Now notice it doesn't even necessarily necessarily need to be in a straight line. It does need to be in the same plane, but the fact that it bends where the pitch of our roof is no problem. So I just want to show you the comparison of the members versus sets of members and how essentially our results are the same. We will again select our load combinations for our ultimate limit to state design from LRFD. Serviceability will be our ASD load combinations, and then we just move down our list. Our materials aren't changing. Our cross sections are not changing. They're all the 8x4 tube. We don't have any intermediate lateral restraints, but the effective lengths we do need to pay careful attention for. So let me jump back to the graphics to zoom out here. For our individual members, now you'll notice we have two separate tables here, members versus sets of members. So we'll first begin with our members. The strong axis buckling defaults to the little member length here. But we have nothing restraining it along this entire continuous member length in the strong axis direction. So this is where we actually want to override this and set this as 32.3. That is the distance from one end to the other because we have nothing, again, restraining it. I hit my F8 key and that will override all four of these members. Now my weak axis buckling, I'm going to leave this as the full member length. I think that this is correct. We have these purlin members framing in here, so our weak axis is inevitably restrained in that direction. The lateral torsional and flexural torsional buckling, again, I'm going to assume that my purlins are restraining it for that type of buckling behavior, so I will leave this as the individual member lengths here. Now moving on to sets of members. Well, we can see here if this is being designed for one continuous member, then the full member length for my strong axis buckling is set at 32.3. This is correct. If we take a look at weak axis though, it defaults to the full member length, but in reality we have these purlin members that maybe we would like to set the length a little bit shorter here for the weak axis buckling. Now the same goes for lateral and flexural torsional buckling. We can set it as the smaller length because of those purlins framing in. The nodal supports, this is only available for sets of members, and I think that this can be a powerful feature when we're designing sets of members. What this does is it places a support at both the member start and the member end here, but what we can additionally do, so node number 19 and 23 are just what we would see back here, 19 and node number 23. What we can additionally do is define where these purlins are framing into the member as fork type supports. So we simply select these different nodes where these purlins are framing in, and the program has a few restraints here, and if it is truly a fork type support, we're going to leave the default here so we don't have any restraint in the global Z direction. But even more so, you can actually specify warping restraint here. So if I check one of these checkboxes and I go to this details, well, this is where we can take into account warp stiffening, whether that's an end plate, a channel section, an angle. So this is huge because it will be taken into account with the design of the member. Now this is not available for individual members, and of course this isn't applicable for a tube shape, but again if we had some type of I section such as this, you can see how this would be beneficial. But one thing to note, if I utilize this nodal supports and I go back into my effective lengths for my sets of members, well, you'll take a look, my weak axis buckling and my torsional buckling have now been grayed out for my unbraced length. And that's because all of that information is now being taken from the nodal supports here. So you have two options. You can manually put in that information, or if you want to define things like warping and such, you can just enter in that information here and the program will override it. The member hinges here, this would just be for a single set of members, either the member start or the member end. If we had a shear release, a moment release, a warp release, we could specify that here. Serviceability data, we want to first select our individual members to compare, and we click OK. Now I'm also going to select from my drop-down sets of members, so we need to make that distinction here so we can select our second or our set of members there. Now, the reference length, these all need to be the same if we're trying to compare the sets of members to the individual members. So, for example, we would want to override this here as the 32.3. We can use our down arrow key in the F8 to override all of those lengths. Now, one more thing before running our calculation, under details and serviceability, I have to change this to the undeformed system. There's no way that I can compare these individual members to my set of members based on these shifted member ends. It's just not comparing apples to apples, so we want to change this to the undeformed system. I click OK. We're leaving the parameters empty as is, and we can run our calculation. So this should solve rather quick, just taking the internal forces from RFEM into our add-on module. And now you should see a few other tables available. For example, we have design by sets of members versus design of members. And of course, we have all of our data available here, but probably what's most efficient in comparing these two continuous rafters is just to simply go to our graphics. If we go to our graphics and I take a look at my individual members that we design versus my set of members, and I'm looking at the ultimate limit state design, it looks identical. Maybe slight differences because we don't have a symmetric structure here, but overall it's really the same code check. We can do the same thing for serviceability. Everything looks almost identical. So that's just comparing members versus sets of members. Now, one final thing to take a look at, if we go back to the module, after we run our analysis, we do have the option here to optimize. All that we have to do is to go back to the cross sections. We can see here our max design ratio is shown as 0.78. We can even go back to case number 1 where we can see all 3 of our members and their code checks. And you can choose to optimize here from the current row, which will simply take all of our rectangular box sections and optimize according to weight to get as close to that 1.0 ratio as possible. Or we can utilize a favorites list again to maybe we have just a few members that we would like to optimize from. So if we choose from current row, we just rerun the calculation, the program will optimize, and then we can export those at the right button and export those cross sections back out to RFEM. So that's essentially how you can optimize within the program. Okay, so that sums up the webinar for today. I just have a few closing remarks. I know that I flew through all of that information. You can always find more information on RFEM, shape thin, and the aluminum module on our website at dlubal.com. We also have a lot of social media sites. One that I really like to point out is our YouTube channel. So it has many other webinars such as this one that were previously recorded that you can just watch on YouTube at your convenience. Our email at our Philadelphia office is info-us@dlubal.com, and our phone number here is 267-702-2815. So if you have any questions about today's webinar or anything else, feel free either to email or to call in. As always, we will have more upcoming webinars. You can register on our website at dlubal.com under support and learning and webinars. Most of you know I always send out an email reminder, a couple of them before these webinars come up as well, so take a look for that within the next month or two. Regarding PDH credit, I am more than happy to issue a certificate. If you could just please email me all of the attendees at today's webinar at info-us@dlubal.com. Again, that's info-us@dlubal, DLUBAL.com. So once I receive the request for the PDH certificate, I will create that and email it back to you. And with that said, I want to thank you for attending today's webinar, and I hope to see you at the next one. Thank you.